Hi, and welcome back to neurobiology in 5 minutes or less. This time we're going to be talking about two of the other really important channels. So far we've talked about sweet receptors, we've talked about umami receptors, we've talked about bitter receptors. So this time we're going to be talking about our salt receptors, and we're going to be talking about our sour receptors. So we're going to start off with salt. So for salt receptors, it's not a huge guess, a really outlandish idea to say that our salt receptors are going to be dealing with sodium. And then the sodium, it's actually an influx. Thus, as it's detecting it, this is going to depolarize your cell, thus creating some sort of signal that can propagate or open up different channels, etc. The interesting thing about salt channels is that this is very true for low salt. However, in things that have a high salt content, we have virtually no idea what's happening. We do believe that, and scientists have studied a lot about this, and scientists do believe that there is an aspect that involves other receptors, specifically some sort of combination between either umami and sour or sour and bitter. They believe that there are active receptors that already exist that are going to be helping take in this high salt content. Bitter in particular, they believe, is involved just because having such a high salt content can be dangerous to your body. Thus, it triggers a reaction very similar to things that trigger the bitter receptors. So that's the deal with salt. And so again, just remember that this is our low salt, and we aren't super sure about how high salt works, but we do think that high salt involves bitter. Moving over to our right, we have our sour. And so sour, and this is sour, but it's also another way to think of it is acidic. So these are acidic sensing channels. So with acids, thinking back to like Bronsted Lowry and those sort of things, and our Lewis acids and bases, we have H plus. So this is our acidic, our proton is our acid detection. And so the basic way that this is going to work is you have an acid and it is going to enter influx into your cell. What's interesting is that both of these models are very different from our G protein coupled receptors. These are both straightforward, where we have an ion in the food that we're eating, whether it's an A plus or H plus, and that is just going to enter our cell and create this depolarizing effect. So it's very different from the other things that we've discussed up until now. What is really cool about the sour is the way that we have a difference between the strong acids and weaker acids like organic acids. So for strong acids, this holds true. We just our acids are able to open up the channel and then come right on in. For organic acids, though, there is a way that they can bind with another protein, and then with this protein, they can actually cross the membrane. And when they cross the membrane, they then, drop off the transporter protein, and then this organic protein actually comes up and can close this channel. And this channel is a potassium channel, so it's a K plus efflux. And it's a K plus efflux, and by closing this, we're again creating that depolarizing effect, right? Because now we have more positive than originally were there, because originally these were flowing out, and now we're trapping them back inside. So it is interesting how the organic acid, even though it's weaker and is not always able to open up this TRP channel, we still have a way that they can work around to still create that depolarizing effect. So this is our salt and our sour, and those are our 5 main taste receptors. So next time we'll focus on a different aspect of our senses.